Picture this. You're an atom, just one lonely atom, drifting past a black hole. Einstein says you'll follow the straightest possible curve through spacetime, the famous geodesic. But here's the twist. You might quietly ignore that rule. A little bit of quantum fuzz could nudge you onto a slightly different route. And we finally worked out the math to show how. So, what did the team at TU Wien do? Instead of tearing up Einstein's playbook, they asked a softer question. What if spacetime stays curved exactly the way Einstein drew it, but the traveler, the particle, follows quantum rules? Think of the path not as a pencil line on a map, but as something woven out of wave functions and operators, the basic verbs of quantum mechanics. From that idea, they carved out a brand new equation of motion, a kind of quantum upgrade to the geodesic. When quantum effects fade away, Einstein's road reappears. But turn the quantum dial up, and you get tiny, systematic detours. Not random noise, real, predictable sidesteps. Now, to pull this off, the researchers had to give up the comforting picture of a single, razor-sharp trajectory. Instead, they followed the entire quantum state step by step through gravity's landscape, and then asked, okay, what does path even mean here? The answer is what they call the q-desic equation. Same spacetime map, brand new legend. Those extra dependent symbols rewrite how the journey unfolds, but never touch the underlying terrain. Let's unpack what changes once the q-desic takes the wheel. First signpost, location gets slippery. Rather than one world line, you're tracking the shifting average and the spread of many possible positions at once. The classical path still sits there as a baseline, but quantum corrections add two things. 1. Curvature-dependent nudges that slide the center of the distribution ever so slightly off course. 2. Terms that tell you how wide or lopsided that distribution becomes as it moves. Second signpost, those nudges aren't one-size-fits-all. They depend on the local gravitational field and on a particle's internal quantum details. Two different kinds of atoms, prepped in different internal states, can feel subtly different pushes even if they start at the same point with the same speed. That's a principled, almost polite, violation of the universality of freefall. Gravity's the same, the sampling of it is finer. Far from massive bodies, spacetime curvature is gentle, and the quantum tweaks whisper so softly that tidal forces and plain old experimental noise drown them out. But crank up the curvature, near a neutron star, say, and the whispers turn into discernible instructions. The math says a delicate probe could peel away from its classical counterpart by a measurable fraction, all while spacetime itself is happily obeying Einstein's equations. Here's the beauty. The construction is conservative. You don't quantize the geometry, you quantize motion inside a fixed geometry, using the standard quantum field theory toolkit. Yet the outcome isn't just the Schrödinger equation wearing a curved hat. The q-desic is built for curved backgrounds, exposing structures you simply never see in flat space quantum mechanics. Okay, enough equations. Let's play with thought experiments. Imagine a supersized atom drop test. Instead of a vertical vacuum tower on Earth, picture a ring-shaped quantum carousel orbiting something ultra-dense. Identical atomic wave packets are released from opposite points on the ring. Classical GR says they should meet perfectly after one loop. If q-desics are real, the reunion point shifts. Interference fringes slide, whispering that each atom read the same geometry with a different rulebook. Or take a space clock built from atoms in a quantum superposition, flown past a compact object along two neighboring routes. Classical relativity worries about time dilation between those paths. Q-desics add an extra layer. Tiny, path-dependent distortions in the interference pattern that actually encodes the ticking. Even cosmology gets a cameo. Picture the early universe. Primordial fluctuations might not just seed density ripples, they could leave faint, history-dependent offsets in how different quantum species threaded the young gravitational landscape. Way too small to spot today, but cleanly described by this framework. If q-desics turn out to be right, the inertial map used by our most delicate instruments needs a revision. Future gravimeters, navigation systems, maybe even gravitational wave detectors would bake in species-dependent corrections. A fleet of cold atom probes, each made of different elements, could become colored threads. Compare how they drift, and you start to sketch the first experimental contour lines of quantum gravity. In short, gravity's traffic rules may come in versions, one for bulk matter, one for delicate quanta. Tomorrow's missions could fire tailored atomic beams like multicolored darts through spacetime, reading mismatches in their landing spots as clues to a deeper script that both GR and QM only hint at. Let that sink in for a second. So here's what we covered today. 1. We kept Einstein's curved spacetime but let quantum mechanics drive the car. That's the q-desic idea. 2. Those q-desics predict tiny, orderly detours that depend on both the gravitational backdrop and the particle's quantum identity. 3. Far away from massive bodies, the effect is hushed. Near extreme curvature, it could be loud enough to measure. 4. Thought experiments, from a quantum carousel to space clocks, offer test beds the next generation of missions could actually build. 5. If confirmed, q-desics would tweak the inertial maps used by high-precision tech, giving us our first experimental foothold on quantum gravity. Here's your takeaway power move. The next time you plan a project, a career step, or even just your week, stop assuming there's one straightest path. Ask yourself, what alternate routes am I ignoring, and what tiny, systematic nudges might push me onto something even better? Because, like our drifting atom, you might discover that the real world rewards those who factor in the quantum detours. Happy exploring, and I'll see you next time.